Hello, explorers. Today, we embark on a grand journey back to the heart of our planet, tracing its origins and evolution through time. This series, split into 4 videos, each representing a quarter of our planet's life, takes us on an incredible voyage from Earth's birth to its present state. You are currently watching the first episode. Before we dive into this new adventure, don't forget to like this video and subscribe to the channel so you don't miss anything. Thank you, and enjoy your journey. Where do we come from? How did the world around us take shape? These powerful questions are engines of thought, answering an instinctual need to understand our origins, our customs, and the world around us. Earth, our planet, is one among others, yet like them, it is unique. Planets share part of their history, but then evolve distinctly, developing their individuality. Earth is the only known planet to harbor life, with organisms that have demonstrated a remarkable ability to dominate their surroundings and adapt them to their needs, humans being a prime example. Humans abhor ignorance, which is why we've delved into these questions early on, initially through philosophy and later geology. The study of the lithosphere reveals astounding information about Earth's formation, allowing us to travel back in time. Today, Earth's history has been written from its inception, but the script is not fixed. It continues to evolve with discoveries. Earth was not always the calm, serene, and beautiful blue planet we know. Its birth and early childhood were in a hellish environment of unimaginable heat within a chaotic orbit. How did Earth evolve to become the world we know today? What was Earth like 4 billion years ago? Join us as we travel back in time, from Earth's formation to the present day, exploring the evolution of our planet. This journey is divided into 4 videos, each narrating a quarter of our planet's life. You're currently in the first episode. Before embarking on this new adventure, remember to like this video and subscribe to the channel so you don't miss anything. Thank you, and safe travels. Welcome, travelers. Today we embark on an in-depth exploration into the mysteries of the universe's creation. We start by understanding Earth, formed 4.57 billion years ago, a significant time after the universe itself was born over 9 billion years earlier. Without placing Earth in the context of the universe and its history, we cannot fully comprehend its place and significance. Let's journey back to where it all began. 13.8 billion years ago, the entirety of matter in the universe was born. An event known as the Big Bang gave birth to not only matter and energy, but also the dimensions of space and time, compressed into an infinitely small and dense singularity. The temperature was extremely high, and all matter organized in this searing environment. 30 minutes post-Big Bang, the universe reached temperatures of 300 million degrees and nearly zero density. For 200,000 years, nothing significant happened. The universe continued to expand, and its radiation prevented the formation of heavier elements, which remained unstable. Hydrogen and helium nuclei swam in a sea of photons for over 30,000 years. When the temperature dropped to 3,000 degrees Celsius, new bonds formed, recombination occurred, and the universe became transparent. This led to the first significant emission of light, known as the cosmic microwave background, a major milestone that has been radiating towards us ever since. 1 million years after the Big Bang, the universe was homogeneous, reaching a temperature of -173 degrees Celsius, devoid of stars, only illuminated by fossil radiation. As it expanded, massive masses of matter moved away from each other. Hydrogen and helium atom clouds began to clump together due to gravity, forming increasingly dense clouds. These proto-galaxies were the precursors to stars. 12 billion years ago, galaxies began to form as islands of matter in the intergalactic void. Stars were born everywhere. A few billion years later, the first galaxy clusters formed. Some of the newly formed galaxies gathered in a cloud, known as a cluster. The embryonic stage of the Milky Way was based on the amalgamation of proto-galaxies. The local supercluster, a gravitational basin in which galaxies and galaxy clusters move, formed 6.8 billion years ago. It resembles a vast cosmic continent, comprising 100,000 large galaxies, each containing about 100 billion stars and 1 million dwarf galaxies, including our Milky Way. 4.6 billion years ago, our solar system began forming. Everything started with the birth of the Sun, the star of our solar system. Dark energy is the main component of the universe. The local supercluster contains over 10,000 celestial bodies, surrounded by the local group, comprising about 30 galaxies, with the Milky Way being the most prominent. The dark matter halo, mostly cold and dilute, made up of stars and gas, forms a thin disk. One of these interstellar clouds, located 27,000 light-years from the center of the Milky Way, is predominantly hydrogen, with a few helium pieces and other heavy elements from a supernova. A part of this nebula suddenly collapses under its own gravity. Atoms accelerate and become hotter and denser, migrating toward the center. The cloud takes on a spherical shape, and the gas heats up to emit energy. The forming sun is still a protostar. To shine like a star, it needs to generate enough energy in an extremely cold environment of 270 degrees Celsius below zero. The gas cloud contracts until it reaches 10 million degrees Celsius at its center. Hydrogen fusion begins. Strong interaction overcomes electrical repulsion, and two hydrogen atoms combine to form a helium atom, releasing energy. 4 million tons of hydrogen burn every second through fusion in a furnace of 15 million degrees Celsius. Photons produced in the sun's core take on the task of releasing this energy, taking 500,000 years to reach the surface. Starting from the burning core, they pass through a cooler and denser radiative zone, followed by a convective zone where hot matter disperses outwards, then cools and sinks back down. Before its final contraction, the future sun is surrounded by a disk of gas and dust, fragments of small bodies. Some of these clump together into larger structures, forming planets. The gas disk thins outward due to decreasing gravity and is continuously fed by the rotating dust around the young sun. Particle movements generate heat dispersed in the infrared radiation range. The solar wind directs gas and volatile compounds towards cooler outer regions. The frost line forms a boundary between the inner world, where water does not freeze, and the outer world, where ice survives. Embryos beyond this line are quite large and succeed in attracting gas, cloaking themselves in hydrogen and helium mantles. They continue to grow, and when the mass of this envelope reaches 100 times that of Earth, they collapse and give birth to gas giant planets like Jupiter and Saturn. An alternative scenario is the dispersion of the planetary envelope, leaving behind a large core of rock and ice, like Uranus and Neptune. On the other side of this line, surrounding gas slowly depletes. Planetary embryos evolve and sometimes intersect. This leads to violent collisions between embryos, each a few hundred kilometers in diameter. These shocks release disproportionate energy. Only 4 bodies will survive, termed terrestrial planets, including Earth. Terrestrial planets form later and slower than gas giants, paradoxically appearing smaller. Each terrestrial planet has a mantle and a core, but each with its unique characteristics. Mercury, closest to the Sun, is followed by Venus, Earth, and Mars. Our main focus is Earth, the planet of our birth. We arrive at the birth of our planet. The story begins with the formation of our Sun, the star of our solar system. Dark energy is the main feast of the universe. The local supercluster, containing more than 10,000 celestial bodies, is surrounded by the local group, consisting of about 30 galaxies, with the Milky Way being the most prominent. The dark matter halo, typically very cold and quite sparse, containing only a few tens of billions of atoms per cubic centimeter, has given birth to a thin disk composed of stars and gas. Formation of Earth. The history of Earth begins here, 4.57 billion years ago, surrounded by dust particles orbiting the young forming sun. These materials, mostly hydrogen and helium in a thin disk interspersed with solid matter clusters, fail to reach the center due to their high velocity. Like dust accumulating behind furniture, these matter particles coalesce and pile up. When they reach a diameter equivalent to at least 800 meters, gravity kicks in, absorbing surrounding dust and forming bodies several kilometers in size. These young, large, planet-like bodies consume all matter in their vicinity, forming planetary embryos. They then collide with each other, merging to birth planets, including Earth. The accretion mechanism of Earth is governed by gravitational escape of larger and larger bodies from a dust disk. This scenario unfolds in 3 stages. Initially, post-Enel near the nebula's symmetry plane collide at low speeds, forming bodies 1 to 10 kilometers in diameter. In the second stage, the attraction of matter to the largest bodies is far more significant than to the smallest, leading to exponential mass increase. This is gravitational escape. Bodies of tens of kilometers evolve to hundreds of kilometers in diameter, a process lasting less than 3 million years. In the third and final stage, Growth ceases once the mass of matter in the feeding zone accumulates. Only eccentric orbiting small planetary-sized bodies remain, a longer phase than the first two. The massive mass of the interstellar cloud, constituting elements, shapes planets. Let's delve deeper into the cosmic materials to determine the nature of Earth's initial chemical element stock. Interstellar dust clouds obstruct light transmission, reducing intensity and altering the spectrum. This proves their composition includes silicates, carbon molecules, and carbon material fragments. However, these dust particles conceal even greater diversity, as each porous allobarat contains elements in micrometric or even nanometric sizes. Some, like nanodiamonds and silicon carbide, are of pre-solar origin. The remaining components of cosmic dust arise from chemical reactions specific to the interstellar cloud or triggered by interactions between the proto-sun and the inner disk. Chondrites, with chondrules, are the most abundant and primitive material of the solar nebula. They contain the original elements from which Earth and other terrestrial planets formed. Comprising microscopic minerals and carbon molecules, chondrites are bound by a matrix rich in calcium and aluminum mineral residues. The journey of chondrules, covered with a thin layer of clay particles shaped like a crown, is possible only beyond the freezing line, where temperatures are low enough not to alter the most fragile compounds. The mineral part of the material consists of olivine and pyroxene, along with hydrated varieties. These clays are mainly magnesium or iron-rich, with little aluminum. Alongside clays, carbonaceous chondrites contain complex organic molecules like amino acids and sugars. So, what covered our 4.57 billion-year-old nascent planet? Carbonaceous chondrites, the most primitive elements formed in the solar nebula, laid the foundation for protoplanets and later planets. The near-perfect match between the compositions of chondrites and the Sun's outer corona suggests Earth's transformation processes, since formation merely redistributes certain elements from one reservoir to another. Earth formed in a dry region of the solar system, far beyond the orbit of Mars, where the system harbors icy bodies or is mineralogically water-rich. Hence, the presence of water is surprising, particularly as Earth is the only planet to possess it. While some of Earth's water originates from meteor impacts, it turns out that the famed chondrules forming Earth also contribute, as they can be rich in water, up to 20% of their mass. Earth's water is a result of a mixture between two different sources: carbonaceous chondrites and comets. The formation of the solar system. The first 100 million years after the birth of the solar system were crucial in shaping the internal structures of planets. The existence of a generalized magmatic ocean marked the start of elements gravitationally migrating towards the centers of the Earth and the Moon. This accumulation slowly forms the core, a differentiation that occurs in as little as 30 million years, indicating an efficient mechanism. What really happened? It all began with a thermodynamic equilibrium separating metal and silicate liquids by their different densities. Continually subjected to a stirring effect, the denser phase gathers in fine droplets, about 1 centimeter in diameter, scattered within the magma. These droplets are then dragged towards the planet's center due to their weight, stopping first at the transition to the solid mantle, where they undergo further compositional changes. They absorb lighter elements than iron, such as sulfur, silicon, or oxygen, However, at a depth of 1,500 kilometers, the pressure exceeds 45 gigapascals, and the temperature, especially around 3,500 degrees Celsius, is crucial to keep the silicates in a molten state. This transition depth is initially determined by the intersection between the melting curve and the geothermal gradient. Iron accumulates, forming pools of varying sizes. Once their masses exceed a certain value, the density contrast is sufficient for them to pass through solid matter in the form of massive drops called diapirs. Their amalgamation gradually forms the planet's core. At the beginning of Earth's history, it was entirely molten. Over time, with cooling, a solid seed forms at the center, where pressure is more significant. The rotation within the metallic liquid generates a magnetic field through the dynamo effect. However, not all siderophile elements are found in the core. The partition coefficient between the two parts varies depending on pressure, temperature, and oxygen content. Subtleties in the chemical equilibria between metal and silicate led to deviations. Only a third of the iron integrates into the core, with a significant amount remaining in the mantle along with other siderophile elements. The formation of Earth's core takes about 30 million years, a short period in geological time, corresponding to the giant collision that led to the Moon's origin. Once the core is complete, it's a liquid iron reservoir, but not yet with a solid core. Its shape is not a perfect sphere, and its center may not coincide with the planet's center. As iron and nickel migrate towards the center, other elements, mostly lighter ones like oxygen and silicon, accompany them, representing about 10% of the core's total mass. The extremely high temperature makes the formation of a solid core impossible, significantly impacting the emergence of life, as the absence of an internal dynamo would leave Earth devoid of a magnetic field. In its primitive state, Earth is a molten lava ball, constantly bombarded by bodies and meteors, each impact melting rocks at the point of collision, reaching temperatures up to 4,700 degrees Celsius on the planet's surface. After 100 million years, the planet's surface becomes coated with a crust of frozen rocks, primarily basalts and comataites, which crack or shift depending on the depth's fervor. The mantle of the Earth is solid, composed partly of olivine and partly of pyroxene. The still relatively high temperature continues to stir convection cells, their viscosities not yet solidifying them completely, allowing continuous deformation. After 160 million years, the generalized magmatic ocean fully crystallizes. The young Earth then undergoes a calmer period with significantly reduced meteoric impacts. When 90% of its mass accumulates, a significant event occurs leading to Earth's current size, the final giant collision with a planetary body named Theia. Continuing its evolution, the young Earth nearly completes its accumulation. After the gravitational escape period, it reaches 90% of its current mass, cools down, and reaches a surface temperature of 1100 degrees Celsius. The solar system continues to be bombarded fiercely by asteroids. Although the accumulation zone is cleared, Earth later undergoes a significant collision with another protoplanet, orbiting in a neighboring path and responding to the sweet name of Theia.